morning. My name is Gerardo. My stage is stage number 1, and I'm going to talk about the kinematic one-dimensional motion. Scalar and vector magnitudes. In this course, we will see another classification of physical quantities, which is established according to the way of working with them, since some of them only have numerical properties, but others also have directional properties. Physical quantities can be classified as scalar and vector. Scalar quantities. They are fully specific by a numerical value and a unit of measure. They have no direction. As example of scalar quantities, we have distance, speed, mass, time, temperature, and many others that, with time study and dedication, you will learn to identify. Vector quantities, or simple vectors. They are specific by means of a numerical value, the corresponding unit of measurement and direction. Examples of vector magnitudes are speed, displacement, force, movement, acceleration, and others that you will also be able to identify as you study the scientific discipline in depth. Characteristics of vector magnitudes. A vector magnitude or simple vector has two basic elements. The magnitude v, which is also called modius, is the extension of vector, is measure or size. The other element is the direction 0. That is where the vector is directed. It is usually expressed in sexagesimal degrees for the position part of x-axis counterclockwise. The application point can also be considered as another element of the characteristics of the vector. However, we will take this point of the origin of the coordination system that we are using. Polar components of a vector. It's possible to find the polar coordinates of a vector, that is the magnitude v, and direction 0. If we know its rectangular coordinate, for this we apply the Pythagorean theorem and tangent theorematic function written as follows. Components method for addition of vectors. Vector quantity can be added, subtract, multiply, and divided. In the course, we will see that vector addition operating, since they do not add the same as scalar magnitudes due to the fact that they have directional properties.
It was learned in the previous part of this lesson that a free-falling object is an object that is falling under the sole influence of gravity. A free-falling object has an acceleration of 9.8 meters a second. This numerical value for the acceleration of a free-falling object is such an important value that is given a special name. It is known as the acceleration of gravity. The acceleration for any object moving under the sole influence of gravity. A matter of fact, this quantity known as the acceleration of gravity is such an important quantity that physics have a special symbol to denote it, the symbol g. The numerical value for the acceleration of gravity is the most accurate, known as 9.8 meters per second. There are slight variations in this numerical value that are dependent primarily upon the altitude. We will occasionally use the approximated value of 10 meters per second in the physics classroom. Freefall. There are two important motions characteristics that are true of free-falling objects. Free-falling objects do not encounter air resistance. All free-falling objects on Earth accelerate downwards at a rate of 9.8 meters per second. As 10 meters per second for back-of-the-envelope calculations. Free-falling objects do not encounter air resistance. Vertical shot. The vertical motion of a projectile is controlled by the force of gravity. This means that there is an unbalanced force acting on the ball, and so the ball will accelerate downwards. Horizontal projectile motion. A projectile is an object upon which the only force is gravity. Gravity acts to influence the vertical motion of the projectile, thus causing a vertical acceleration. The horizontal motion of the projectile is the result of the tendency of any object in motion to remain in motion at constant velocity. Due to the absence of horizontal forces, a projectile remains in motion with a constant horizontal velocity.
My name is Melissa and I'm going to explain the stage number 3, named kinematic circular motion. Linear displacement is the movement of an object along a single axis in a straight line. Angular displacement is the angle described by a body in a circular motion. Some data you must remember are 360 degrees are equal to 2p radians, and 1 radian is equal to 57.3 degrees. Now, linear and angular velocity. Linear velocity is the ratio of position change with the time, also known as tangential velocity. Its formula is velocity equal s over time. And angular velocity occurs when a particle or an object moves along a circular path in a time interval. It is defined by the rotation ratio and is represented by the letter w. The formula is angle over time. Now we have frequency and period. Frequency is the number of cycles per unit of time that a body does in vibratory or undulatory movement. It is represented by the letter f, and it is expressed in revolutions around the center of rotation. Its formula is F equal number of revolutions over time. And period is the time it takes to an object in a circular motion to complete a revolution. And the formula is Time is equal 1 over frequency. All the objects that rotate in a curved trajectory have an accelerated movement. The formula of the centripetal acceleration is rw to the square. Finally, I have an example of this topic that says a ball is attached to a string that is 1.5 meters long. It is spun so that it completes 2 full rounds every second. What is the centripetal acceleration felt by the ball? We are simply asked to find the centripetal acceleration, which is given by the formula velocity to the square times radio. And we were given already the radio, which is the length of the string, 1.5 meters. So we only have to find the velocity of the ball. So we must use the formula 2p times the radio. Then we substitute the 1.5 in the radio and we get 3p. Now the velocity can be found by multiplying the distance by the frequency, which will be 3p times 2, because remember it will be 2 full rotations. So the result is 6p meters per second. Now that we have all of our variables, now we have to plug onto the first equation, which is 36p to the square divided by 1.5, giving the results of 237 meters per second to the square.
Hello, my name is Sofia and I'm going to talk about the stage 4 dynamics application of Newton's laws. In order to have a good result in the application of the Newton's second law of motion, we need to know and recognize all the forces acting of a body. We must make the corresponding free body diagram, which consists of a graphical representation in a coordinate system where we place all the forces acting of an object. Motion on a friction-neutral plane. For a vector analysis of forces and problem solving, we need to develop a free body diagram. The general procedure in the development of a free body diagram is: number 1, identify all the processes acting on the body and determine whether the motion is on a horizontal plane or in the vertical plane. Number 2, draw the diagram in the body with the forces identified in the previous step. Number 3, if there are forces, if any of the quadrants, they decompose into their rectangular components, Fx and Fy. Friction force. This term is commonly used thinking that is another type of force of nature. However, the friction force is due to a comfort natural resistance to sliding between materials in contact or within a medium, due to friction between molecules. Friction force opposes the sliding motion between the contact surface and follow a direction parallel to them. That's it. The frictional force is proportional to the compression force, and as we saw, the compression is numerically equal to the normal force.